In the beginning, everything was confusion and darkness. Suddenly, light appeared. The most dense point transformed, and with this transformation came all different kinds of particles, matter, and antimatter. In one point, everything started to align. The matter raised the fight against antimatter. All the physical laws started to work, and the clock of the stars was on. The Earth started to exist and breathe in its own way, and our star, the Sun, heated the Earth's surface since it was born. The life on Earth began and flourished, and the human era started to shine. In the present, humans have been wandering and making trips to our nearest planets. But one of the things that stops us from doing those missions is the fact that we as organic individuals can't support big amounts of radiation. The question here is, why the radiation affects us outside the planet and not in the planet? In this video, we will explain how Earth is protecting us against radiation, and specifically against gamma radiation, explaining its generation and how these rays decay.
Stepping into the topic, let's first expose the effects of radiation in human bodies. The most common effects for exposure to radiation are leukemia, lung cancer, especially for uranium miners, and skin cancer. Also, we can see deformation in embryos and maybe some mutations that we cannot know, like maybe Hulk. But everything depends in several factors, such as the dosage or maybe the time exposed to the dosage. Also, we can say the kind of tissue or cells that are being directly affected. And everything is totally proportional to the health of the person and the age.
Continuing through radiation, we can find that there are important emitters of high-energy radiation, and we can see some examples. Neutron stars. And we can see the huge amount of energy that they emit. Also, we can see supernovas and even the moon. And that came in different shapes, like UV rays, X-rays, alpha emissions, beta emissions, and gamma emissions. In fact, one of the biggest emitters of radiation is one of our biggest companions in our lives, the sun. From the sun, we get a very full and extensive spectrum of electromagnetic radiation, and we got from radio waves to gamma rays.
But we need to make a point here. The vast majority of gamma rays that are coming from space to our planet Earth aren't coming from our sun. Well, today we don't have a sun, but almost every day we have a sun. In fact, the sun almost never emits gamma rays because the ones that are produced are hit with a huge amount of matter in their journey to get out of the fusion nuclear factory that is our star. And that makes the gamma rays become way less energetic. That's the photoelectric effect, and we'll be explaining it in a few moments later. Also, there are a vast amount of gamma rays coming from the sun that do arrive to Earth, but a major quantity of those, just not to tell all, are produced in exceptional events, like a huge solar wind or coronal mass ejection.
We thought that it was important to remark that almost all damaging radiation coming from the sun to the Earth is UV radiation, some X-rays and alpha and beta emissions also. The way that alpha and beta emissions don't affect us that much is because of our magnetic field. Why is that so? Because those types of radiation are positively or negatively charged. The alpha radiation or alpha particle is a nucleus of helium-4, so it is positively charged, and the beta radiation is an electron or positron that has been emitted in an energetic collision, and it is also positively or negatively charged. Those kinds of radiation can be deflected or absorbed by the magnetic field in Earth that is generated because of the moving nucleus at the core of our planet. This effect of deflecting radiation creates a beautiful spectacle to the human eye. The auroras, or the northern lights. In the south, they know them as southern lights.
And here is where we get to our main questions. Why is gamma radiation so dangerous? How is the gamma radiation the most energetic kind of radiation don't get to us. Starting to why it is so dangerous, let's make a simple example. There's this effect called photoelectric effect that describes what happens when a photon hits an electron. The experiments had told us that some of the energy that's in the photon is transferred to an electron in the form of kinetic energy. This effect is described by this formula here. You can see. There you go. Here we can see that the maximum kinetic energy is equal to the Planck constant multiplied by the photon frequency and a subtracting work function that is particular to different elements. And this gives us the minimum energy required to move an electron of its kind. In a way, we can identify materials through these experiments. Also, we know that the work function is equal to the constant of Planck specifically, multiplied by the minimum energy frequency that starts to move an electron. So, at the end, the formula will look like this. However, it's important to also explain the Compton effect. This is, when a photon hits an electron, it shifts and changes direction. This change of direction is given by an angle, and it's because of this crash.
Arthur Holly Compton, which name is in effect, was the one who made the formula that described this, which makes a direct relation between the difference in the wavelength and the scattering angle. And knowing that the change of energy in a photon depends directly on the change of its wavelength, then we have a clear path to follow. So knowing this, we can tell you why this kind of radiation is so dangerous. The gamma rays are so energetic that moving one electron of an atom is not that of a hard job. Let's see, for example, the bond energy in a normal O2 molecule. If we take the energy of some tables, we will see that it is 498 kilojoules per mole. So, making a little change to have just one molecule by doing this, we will obtain that there's a bond energy of 5.26 electron volts per molecule. Now, let's take the energy of a simple gamma photon that has a wavelength of 10 picometers. By substituting it in our formula with the constant of Planck and the speed of light, we will obtain that our photon has an energy of 124 kilo electron volts, which is a lot higher than the energy that is required to the O2 to be bonded. So, if these photons hits those electrons that bond this molecule, they will rip apart. So, knowing this, what do you think that some energetic photons like this will do to your body? Well, the molecules in your body will break apart just as the O2 molecule will break apart.
So, how are we protected against gamma rays? Well, thankfully we have a beautiful and dense atmosphere. And maybe you are thinking, what does that mean? The solution is easy and totally related with all what we have been describing. The gamma rays coming from the sun, neutron stars, pulsars, and supernova explosions need to go through a very thick and sufficiently dense atmosphere that really shields the planet. How? Because the gamma photons crash with a lot of electrons and atoms in its way to the ground, making them less energetic with each of the collisions that they suffer.
This can be described with a simple equation of decaying energy, where the energy is proportional to the starting energy, the thickness of the atmosphere, and its density. In fact, that's one of the reasons why astronauts cannot be in space for long periods of time, because the layers of the spaceships and the layers of the spacesuits are not enough to stop this kind of radiation. Can we solve this someday with a different type of technology so we can stay longer periods of time in space? Or if we will continue going to the space, are we going to evolve so gamma radiation will not affect us? We don't know yet, but it's a fact that everything is in constant change. And if we think about it a little bit, we can realize that we have the best protection against gamma rays, our atmosphere.
When two neutron stars collide with each other, it creates a black hole, and in the process, a gamma ray burst is emitted perpendicular to the magnetic spiral of the orbit before the collision. If it happens less than 10,000 light years away from Earth, a complete side of the atmosphere would be ionized instantly, and gamma rays would reach the surface, potentially leading to a mass extinction.
Wait, before you leave, make sure to smash that like button and subscribe to the channel. Thanks.